Hi everyone, my name is Kate Bilid of BSEC 3A, and today I'm going to present to you my performance task number 6 in ECE 23. If you remember, we learned about the convolutional coder rate 1 over 3. So for this video, we're going to discuss the convolutional coder rate 1 over 3. So coding provides us with a way to introduce redundancy into a signal that we can exploit to counteract the deleterious effects of noise in the signal as it passes through a communication channel. For this illustrative example, we shall use a simple convolutional coder described in this slide. So the way this works is that the message bits are shifted in on the right hand side, and the modulo 2 adders produces the coded message. The code rate R for a convolutional code is defined as R equal to K over N, where the code rate K over N is expressed as the ratio of the number of bits into the convolutional encoder to the number of channel symbols output by the convolutional encoder. So for this, we're going to determine the transition table, state machine diagram, and the trellis diagram of this convolutional coder, which is rate 1 over 3. Now from this design, I am going to show you the generator representation, which shows the hardware connections of the shift register taps to the modulo 2 adders. A generator vector represents the position of the taps for an output. A 1 represents a connection, and a 0 represents no connection. So let's say, for example, G1 stands for these links here. It is 111 because it connects to the input and the output of the two modulo 2 adders. If this is our G1, then our N1 will be equal to data XOR S0 XOR S1. For G2, it is 0, 1, 1 because it is only connected to S0 and S1. Here means that G2 is not connected to the input. With that, our N2 will be equal to S0 XOR S1. So same goes for G3. It is 101 because it is only connected to the input and the S1. So with that, our N3 will be equal to data XOR S1. Now that we know the basics, let us perform. First, let's determine the transition table. Now when the first clock arrives, S0 and S1 are 0, 0 because shift register inputs will be reset. So for the first 2 bits, first iteration or first clock, the input data is 0. So if our input data is 0 at state 0, 0, 0 at state 0, 0, what will be our V1? So V1 is data XOR 0 XOR S1. So 0 XOR 0 XOR 0 is equal to 0. Next, what's our V2? So V2 S0 is S0 XOR S1. So we're going to XOR 0 XOR 0, which is equal to 0. Now for V3, it is data XOR S1. So 0 XOR 0 is equal to 0. Now that we know our outputs, what will be the next state? So based on the present state, we can determine our next state depending on the input data because input data is shifted to S0 and the content of S0 is shifted to S1 and the content of S1 is shifted and then discarded. Now, if the data is 0 and S0 and S1 is 0, then the next state will be 0. So this is how it works. Next. So same process, V1 is data XOR 0 XOR S1. So 1 XOR 0 XOR 0 is equal to 1. V2 is 0 XOR 0, which is equal to 0. V3 is 1 XOR 0, which is equal to 1. So what will be the next state if our input data is 1 at state 0, 0? So it will be 1 0 because the input data 1 has been shifted to S0. And the 0, the previous 0 from S0 has been shifted to S1. And this 0 from S1 has been discarded. So the new state will be 1 0. So same process applies in determining the outputs in the next state. Basically, we do XOR operations in determining our output based from the input data and the present state. And in determining our next state, we do bit shifting by 1 bit. And the shifted bit is discarded. So this is our complete table should look like. Same process apply. Now in this slide, I'm going to show you how to design the state machine diagram based on our outputs, input, present state, and next state. So we have 4 states, that is 0, 0. By the way, I prefer to place my states in a diamond form. So 0, 0, 0, 1, 1, 0, and 1, 1. So let's start with state 0, 0. If the input data 0 arrives, then the next state will still be 0, will still be 0. So the arrow will still be pointing to itself with this condition that if the input data is 0, the corresponding output will be 0, 0, 0. Next, in the present state, from 0, 0, if the input data 1 arrives, it will transition to 1, 0, 0 with a condition that if the input data is 1, the corresponding output will be 1, 0, 1. Next, from the present state 0, 0, 1, if the input data 0 arrives, the next state will be 0, 0 with the condition that if the input data is 0, the corresponding output will be 1, 1, 1. So still the same reading and processes apply. So basically a new input data bit causes a transformation from one state to another, and the path information between the states represents the input information or the input data and the output encoded. So this is the finished product should look like. One. So now the trellis diagram representation. So here we have our T at 0 and T at 1, each representing the 4 states. So basically, a trellis diagram is a redrawing of the state machine diagram. It shows all possible state transition at each time step. So now let's start from 0, 0 state. Let's start from 0, 0 state. When the first input data 0 arrives, the state remained at 0, 0 state with a corresponding output of 0, 0. Second, from state 0, 0, when input data 1 arrives, the state transition from 0, 0 to 1, 0 with the output of 1, 0, 1, 0, 1. Third, from state 0, 1, when input data is 0, the state transition from 0, 1 to 0, 0 with the outputs of 1, 1, 1. So the same process in reading applies. As I've said, this is just a redrawing of the state machine diagram. So this is our finished product. So this is all for the discussion today. Thank you.